Hello, my name is Josh Kramer, and today I will be doing my Transport 1 homework 4, which is we have this pipe system here with a pump, and so we have two levels where the fluid's going to be. We have this upper level and this lower level. The pipe, where the fluid flow direction is going up this pipe into this reservoir and then back into this original level. And so we have some measurements here. So the length and the water height to the floor is 1 meter on the bottom level, but at the top it's 3 meters. Between the bottom of the top reservoir to the top of the water level at the bottom reservoir is 6 meters. And the difference in heights and water level is 9 meters, and we have a pump that's pushing up this fluid going up here. So we're going to look at two different point comparisons here. We're going to look from point 1, which is at the water level at the top reservoir, and then going down to 2, where the water is where the fluid is emptying out into the bottom reservoir. And then the second system we're going to be looking at is from point 3 to point 4. So from the water level at the bottom reservoir to where the water is emptying out at the top reservoir. So the question is asking essentially, how much power is being supplied by this pump here to keep the system circulating, and will we require a chiller to maintain temperature in the system? So we can assume that at the bottom here is actually negative 10 meters, and at the top here is 0 meters. And some other assumptions we're making are that this system is a steady state system, which means that the fluid in is equal to the fluid out. And we're going to be using the Bernoulli's energy balance equation, which says the change in pressure over density plus the acceleration due to gravity times delta z, so the change in height, plus the difference in velocity squared over 2 is equal to the work of the non-flow over the mass flow, plus this factor here, which we will not be using because we can assume that our piping systems are perfectly insulated. So we can go ahead and we're gonna start the comparison between point 1 and point 2. So we're gonna start writing out this Bernoulli's equation. So we have P2 minus P1 over rho, and this is that's the density of water, and that is plus the acceleration due to gravity times Z2 minus Z1, and that is plus the velocity of 2 squared minus the velocity of 1 squared all over 2, and that says that is equal to the work over the mass flow plus this factor here. So since it's insulated, this factor is 0. We're not gonna have any work done because it's being pulled down due to gravity. There's no pump pushing it up or really pushing it down, because it's just happening automatically. So there's no work there. Additionally, there is no pressure at 1 because that is exposed to the atmosphere, so that's 0. And at Z1, because of this, what we wrote here, that level is 0 meters. That is 0 as well. And then we can say that the velocity at 1 is also 0 meters per second. So moving on, we have these things. Now we have our simplified equation. So let's just rewrite it back out. We have P2 over rho plus G at Z2, and we know that is at negative 10 meters. And that is plus the velocity at 2 squared over 2. I can write that better. And we know that that's equal to 0 since both sides of this equation is equal to 0. All right, so Now we can, we need to go ahead and write that rho GH over rho. This is the equation that we're going to write. And the densities cancel out here. And so we know that the height is 1 meter times the acceleration due to gravity. So, and then we come over here, we're going to do 1 meter times the acceleration due to gravity minus 10 times the acceleration due to gravity plus v2 squared over 2 is equal to 0. Which means that we have -9 due to the acceleration, times the acceleration due to gravity plus v2 squared over 2, which means that v2 is equal to 18 times the acceleration, square root of 18 times the acceleration due to gravity. That is what v2 equals. And so now we can go ahead and we're going to try to solve for our flow rate for these two at 2. And we know that the flow rate is just equal to the velocity times the area at 2. And so we know V2, and then the area is going to be dependent on the pipe diameter. So that's pi r squared. And speaking of R, we know that R, when you what the equation is giving us is what the diameter of the pipe is, and so by doing some dimensional analysis, you can determine what R is, and so R is equal to 0.127 meters. I don't know why that was so hard for me to say. And so then all of this is equal to square root of 18 times G times pi R, 0.127 meters squared times the density of water. All right, so now let's move on to comparing position 4 and position 3. So we have P4 minus P3 over rho plus G times Z4 minus Z3 plus V4 squared minus V3 squared all over 2 is equal to the work over the mass flow plus this this factor here, so that factor is 0. So the velocity is 0, and we know that the pressures are also equal to 0 because they're both exposed to the atmosphere. So now we can go back and rewrite this. So we have G times Z4 minus Z3 is equal to our work. And we do have work this time because we have to account for the pump. So the pump is doing work to maintain fluid flow. And so now we know that we're just going to bring this mass flow over. So we have our mass flow times gravity times Z4 minus Z3 because we are going to solve for our work. And we know that this value is equal to 9 meters because of this measurement that we already have from our diagram. It's 9 meters. So going forward, we're going to use this and solve for our power. So power is going to be equal to the density of water times the square root of 18 times the acceleration due to gravity times that area. So it's going to be pi r, so 0.27 meters squared times 9.8 meters per second squared, acceleration due to gravity, times 9 meters from up here. All right, so a few more things that we need to substitute is that the density of water is 1,000 kilograms per meters cubed, and then G here is of course 9.8 meters per second squared. And it looks like, okay, so it looks like that's everything that is left. So our power, if when you multiply all of this out, is equal to 60,000. And we can go back through here and look through all of our units here. So this is going to simplify down to meters squared times the kilograms over seconds cubed, which is equal to joules per second, which is equal to watts. And doing some more dimensional analysis, we can, if that's equal to 1 watt, then we can say, so 60,000 watts is also equal to 60 kilowatts. And that is our final answer. We have 60 kilowatts of power that is needed for this pump. And so the question is, do we or do we not need a chiller to maintain temperature in this system? So the answer is yes. And the reason that we need a chiller, so chiller is needed. The chiller is needed because when you supply power through a pump, that energy is being converted into the system as heat, which is going to increase the temperatures of the water, and you're going to need a chiller to bring the temperature of the water back down to where you want it to be. Otherwise, the temperature of the water is going to continue heating up. Eventually, it will start boiling, and you won't have water anymore. You will have steam. So that is all we have here. Thank you very much.